If you want to experience physics firsthand, I recommend this activity known as ice blocking. You might be familiar with it. We used to do this a lot in high school. You go to a lot of convenience stores or liquor stores will sell you a large block of ice, just big enough that you can sit on it and you can put a beach towel on top. You take it to the top of a grassy hill, and then, of course, gravity pulls straight down toward the center of the earth. But if we make an x-axis that runs parallel to the incline and a y-axis that points normal or perpendicular to the incline, then that force of gravity has components along the chosen x and y axes, and one of those components to gravity provides for your acceleration down the hill. And it turns out there's not a whole lot of friction between a melting block of ice and the blades of grass. So it ends up being a pretty good study in applying Newton's laws. So let me diagram that a little better. So let's think about all the forces that are acting on a block of ice with a mass of m, sitting on a hillside inclined at an angle of theta. Right, so we can make a force body diagram or we can make a free body diagram. The difference is on a force diagram, you just draw all the forces on the actual picture, right? So pulling down at the center of the block is the force of gravity. Acting at the surface is a force that can only point perpendicular to the surface itself, so we call that contact force a normal force. So we got normal force, we've got mg, and then that's it. I think ice blocking is a good example of as close to negligible friction as you can get. If there really is some friction, then we draw a force pointing back this way, but let's say that ice blocking has such little friction that we ignore it. So given those two forces, what's the net result? Maybe it's better to actually make it a free body diagram. So we just say that dot represents the ice block. Now it's typical, what we've done up till now, is make x and y axes that are horizontal and vertical. Okay, so that's one option, but it's convenient to let the x-axis be the axis along which the object accelerates. So I would choose a different xy axis. And this comes down to frames of reference. You not only have a choice of what you think of as being positive and negative directions, but you have a choice of what you consider to be the x and y axis. The only real rule is that the two axes have to be perpendicular to one another. So let's do this. Let's say the x-axis is the axis along which the block accelerates, so it runs parallel to the incline, and then the y-axis, well, the y-axis would coincide with the direction of the normal force. Oops, didn't need to erase that little part. Draw that back in. X-axis, y-axis. And so you see the normal force doesn't need to be broken into components. We don't need to resolve that force vector. It already lies along one of our axes, but the force mg has components along the negative x-axis and the negative y-axis. So let's just draw this again, free of the object. So our x-axis points that way, y-axis points this way. There's the normal force. And then there's a component of gravity along the negative x-axis. Actually, there's no reason to call that negative. I guess we could say that's the positive x and that's the negative x. So lots of freedom in your frame of reference. Once you choose, you're stuck with that choice. Okay, there's a component of gravity along the y-axis. Now let's see if we can figure out what to call these. I'm going to go back and clean this up a little bit. Okay, so how about this? This is a typical way to do it. We make a line that runs through the tip of the vector that we're trying to break into components and runs parallel to each axis. So if I make a line through the tip parallel to the x-axis, then I can see how long one of the components of gravity is. And then in the same way, I can make a line that's parallel to the y-axis and runs through the tip of the vector that I'm trying to break into components. And so I can figure out how long the component is along the x-axis. Now if I take that vector on the x-axis and draw it down here, it's still a vector that has the same length and points in the same direction. And so I think you see the same thing I see. There's a right triangle. So the right triangle has a hypotenuse with a magnitude of mg. That's the length of our original vector. So if, well, let's do a little investigation of angles here. Let's just say, for example, this is 30 degrees. Then the vector that represents the weight, mg, is pointing straight down. We know that direction forms 90-degree angle. And so this angle right here would have to be 60 degrees, but from that component to that component that I'm highlighting, that all has to be 90. So you see, this angle theta has to be the same thing as this angle theta. Do you follow that? That's pretty straightforward geometry, right? Or imagine if I draw an incline that's a much smaller angle. So if theta becomes smaller, don't I get something like this? mg points straight down, but now the line normal to the surface and parallel to the surface makes this angle smaller, right? This theta gets smaller in the same way this one gets smaller. So I'm just trying to say that the theta right here is the same as this theta. So then the component that we have in orange is the one adjacent to the angle theta. So this would be mg. Okay, SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. So we always associate cosine with adjacent. So this is mg cosine theta. So that must mean the other component is mg sine theta. All right, so where were we? On our resolved free body diagram, there's a component mg cosine theta that points opposite the normal force, and there's a component of gravity, or the component of the weight of the block, mg sine theta, that points parallel to the incline. Okay, so I think it's pretty clear that the normal force and mg cosine theta cancel one another out. You would never do this activity of ice blocking, put your ice block on the hillside, sit down, and then as soon as you lift your feet up, accelerate up along the y-axis, right? Your acceleration is only going to be along the x-axis. So we know that there's an equilibrium along the y-axis, but there's an imbalance of force along the x-axis. So we can argue that the normal force has to be equal, in this case, to mg cosine theta. So the net force along the y-axis is 0, but the net force along the x-axis is definitely not 0, and in fact is just equal to the remaining component of force, mg sine theta. Well, now think about that. By Newton's second law, we're allowed to replace net force with ma. So ma equals mg sine theta. If we divide both sides of the equation by m, we find the acceleration of an ice block should be very nearly equal to g sine theta. Now let's check if that makes sense. Let's consider two extreme inclines. Imagine going ice blocking down a hill this steep. Okay, you'd never do that where theta is really, really large, right? Here theta is approaching 90 degrees. So if this equation is correct, the acceleration in this case would be g times, well, sine of 90, or very close to it, and the sine of 90 is about 1. So in other words, as the incline becomes nearly vertical, the acceleration becomes nearly 9.8 meters per second squared. Now imagine going ice blocking on a hill that's almost just flat ground. Okay, so now we're taking the sine of nearly 0 degrees, which itself is 0, so the acceleration is nearly 0. And wouldn't that be the case if it was flat? So this seems to make sense. The acceleration of an object on a frictionless incline. That's what we have here. That's the point of illustrating this example with ice blocking, where the friction between the melting block and the grass is negligible. On a frictionless incline, the acceleration of an object is acceleration due to gravity times the sine of the angle of the incline. So one more time, whenever dealing with motion along an incline, we don't make the x-axis horizontal, we make the x-axis parallel to the incline. And therefore the y-axis must be perpendicular to the incline. So when the only forces acting are gravity and normal force doesn't need to be resolved into any components, but we replace mg with a component along the y-axis and a component along the x-axis. But you can see those components are nothing more than the sides of a right triangle, so the component opposite the normal force is mg cosine theta, and the component parallel to the incline is mg sine theta. Normal force and mg cosine theta cancel each other out, so the net force is mg sine theta, which leads to the result acceleration is g sine theta. Let's see if we can put that into practice. A 60 kilogram snowboarder moves down an incline that's 30 degrees. Once again, this is a frictionless case, and there's constant velocity. So there may be no friction, but there is air resistance. Okay? Otherwise, the velocity would be constant. You would have an acceleration equal to g sine theta. What is the force of air resistance? Okay, there's our incline. Here's our snowboarder. The angle's 30 degrees. The mass is 60 kilograms. And they're traveling down the hill with 0 acceleration, or in other words, constant velocity. What's the force of air resistance? Let's make it a free body diagram. So let's put a dot here to represent the snowboarder. So one of the forces acting is gravity. Another force acting is the contact force, or the normal force. And then we're also told that there's some amount of air resistance. So that would point, well, let's draw in our x and y axes. There's the x-axis. The y-axis is always in the same direction as the normal force. So we've got this third force back this way. Call that F subscript air. So the only force we need to break into components once again is mg. So we've got our first free body diagram, which is unresolved. Draw a second free body diagram that's resolved. X-axis, y-axis, normal force, air resistance, a component of gravity parallel to the incline, a component of gravity perpendicular to the incline. Now in this case, notice I drew the normal force just as long as the component of gravity perpendicular to the incline, which we calculate as mg cosine theta, so those cancel out. And notice that I drew the other component of the weight, mg sine theta, just as long as I drew the vector for the air resistance. And you know why? Because we were given the hint that velocity is constant. So constant velocity is one form of equilibrium. Remember, there's really two forms of equilibrium, either at rest or moving at constant speed. But in the end, equilibrium always means the sum of all forces is zero. So any forces in opposite directions have to all be equal length. So this is a case where all the forces cancel one another out. So if we're asked to find out how strong is the force of air resistance, all we really need to do is calculate what's the component of the weight of the object parallel to the incline. And so it's m times g times the sine of the incline. In this example, it's 60 kilograms times 9.8 meters per second squared times the sine of 30 degrees. Grab a calculator, let's see what we get. We get 294 newtons. Okay, one more example problem for forces on an incline. This time it's a 80 kilogram hiker standing at rest on a 35-degree incline. Draw a free body diagram with all the forces resolved into their components. So that dot represents the hiker. There's normal force. There's weight. And again, if this were frictional, I'm assuming they're wearing hiking boots, right, that grip the hillside. So this is not like ice blocking. This is not a case of frictionless. So there is no acceleration equal to g sine theta. In fact, since they're at rest, the acceleration is zero. So they must be relying on some force of friction pulling this way. But the problem asks us about making a free body diagram with resolved forces. So a reminder that the x-axis points this way, parallel to the friction force. The y-axis points this way, parallel to the normal force. So mg needs to be broken into its components. So we'll draw it again. X-axis, y-axis. There's one component of gravity, mg sine theta. There's another component of gravity perpendicular to the incline, mg cosine theta. There's the normal force. And lastly, there's the friction force. And again, I've drawn all these forces in opposite directions equal to one another so that they cancel each other out. So the normal force and mg cosine theta cancel, and mg sine theta is canceled by the friction force. Okay, so at least we drew the resolved free body diagram. We answered the first part of the question. Next one is, what's the magnitude of the hiker's parallel component of weight? So what's the value of mg sine theta? So this time it's 80 times 9.8 times sine of 35 degrees. I guess I should have units in here. These are kilograms, these are meters per second squared, but a kilogram meter per second squared is a Newton. 80 times 9.8 times the sine of 35 gives us about 450 newtons. What's the magnitude of the normal force? Well, in this case, the normal force must have the same magnitude as mg cosine theta. So we plug in all the given values, and that calculates to 642 newtons. You can double check that on your own calculator. What's the magnitude of the frictional force? Because we're told that the hiker stands at rest, and we see in our free body diagram the friction force has to cancel mg sine theta, then we can just copy our answer and say that must be 450 newtons as well if everything's going to cancel out. Last problem. Well, wait a minute, we've done all our inclines the same way. Is it any different if the incline runs in this direction? I should think not. So, just for the sake of it, let's draw the incline angled the other way. A 70 kilogram physics student goes down a grassy slope by riding on an ice block. Okay, so back to the original ice blocking problem. $30, 70 kilograms, 10 kilogram ice block. How much time will it take to reach the bottom of the 25-meter long slope? So they have to travel 25 meters down the incline. We're asked for an amount of time. Okay, let's make a free body diagram. That's normal force. That's mg. And in this case, there's no air resistance, there's no friction. When we reference ice blocking, it's just an attempt to say we have a problem where we can ignore those other forces. There's the x-axis, there's the y-axis. So only mg needs to be broken into its components. Normal force points that way, and the component of gravity or the component of weight opposite the normal force is always mg cosine theta. And so we're left with a component of the force parallel to the incline equal to mg sine theta. Those forces cancel one another out, so the only amount of net force or unbalanced force is mg sine theta. So if the net remainder force is mg sine theta, but net force according to Newton's second law is the same thing as ma, then again, there's a red herring here. We don't really need to know the 70 kilograms or the 10 kilograms because mass cancels out on both sides of the equation. So once again, we've rederived the formula that for the case of zero resistive forces, an object on an incline accelerates at a equals g sine theta. Now 30 degrees is a convenient angle because it's the special angle for which we know the sine of theta off the top of our heads. It's 0.5. So here we have a case where the acceleration is 9.8 meters per second squared times 0.5, which gives us 4.9 meters per second squared. But we're asked for time, we're not asked for acceleration. So now it becomes a kinematics problem. The initial velocity is 0. We're asked for time. We're given acceleration. Remember, we were also given displacement along the x-axis as 25 meters. So with all these values, the equation we want is delta x equals v initial times time plus 1/2 at squared. Since the initial velocity is 0, that part of the equation goes away. And we do the algebra to rearrange for t. We get time is equal to the square root of 2 delta x over a. So we plug in the given values. This is the square root of 2 times 25 meters divided by 4.9 meters per second squared. Pay attention to the units, and the meters cancel out. We have the inverse of square seconds, which gives us square seconds, but we're taking the square root of all of this, so of course our units are going to give us just what we want since we're trying to solve for a time value. And according to my calculator, the answer is about 3.19 seconds to reach the bottom of the hill. So there you have it. Forces on an incline are a good example problem that forces us to treat force as a vector quantity. So this all seems pretty easy at first, right? Newton's second law seems like it can be expressed as F equals ma, but that's a little short-sighted. It's not any singular force that's equal to ma. We have to take the combination of all forces. Sometimes the combination includes gravity. Sometimes normal force factors in with the combination. Sometimes air resistance. Sometimes friction, etc. The list goes on. And we have to find a way to combine all the forces together if we want to know the acceleration. But the forces don't combine as simple scalar math. Combining the forces is a exercise in vector mathematics. And then lastly, this is still a little too simplified. It's only the external forces that need to be summed up. And in our next few lessons, we'll give some more examples of the difference between internal and external forces. So Newton's second law seems very simple at first glance, but if you can appreciate this idea that force is a vector quantity, you can see there's often a little bit of challenge in diagramming in order to help figure out what exactly is the value of sigma f.